Hello and welcome to example 4 of Siemens TI Portal Lateral Logic Programming course. In this example, we have a problem that is related to digital electronics. If you get chapter where two variable is either ANDed, ORed, or exclusive ORed, or inverted or complement is created. Here is the problem. I will go through step by step and describe it. Write a program that ANDs Bit0 with Bit2 when DI1 is energized, ORs Bit0 with Bit2 when DI2 is energized, exclusive ORs Bit0 with Bit2 when DI3 is energized, and complements Bit0 when DI4 is energized. Bit1 is to hold the result in each case. If more than one input from DI1 to DI4 is energized, only one of the operations will be performed. The precedence order for operations would be from AND, the highest precedence, to complement the lowest precedence. We have four operations: AND operation, OR operation, exclusive OR operation, and complement operation. And each operation is executed after pressing a digital input DI1 to DI4. So DI1 activates AND operation, DI2 OR operation, DI3 exclusive OR, and DI4 complements. We are assuming that these inputs are normally open type, and then we have one byte allocated where we will use bit 0, bit 1, and bit 2 from this byte. Let's revisit our theory of digital uh, logic, gate logic. Now this is OR operation. In ladder logic it should be like this. In digital electronics we used to learn about the symbols, and it is the symbol of OR operation. In ladder logic TI portal, I will show you immediately after going through this. This is the OR operation in ladder logic programming, and in chart we used to show like this. We have two inputs and one output, and then we have AND operation. In AND operation, okay, let's just read the sentence. Parallel contacts are equivalent to an OR gate. Series contacts are equivalent to AND gate, and this AND gate in ladder will be like this. Have contact bit 0 and bit 1, and it in series, and then output will get that. So both inputs are 1, then only the output will be 1, like this in chart. And exclusive OR is the same like OR chart, except that when two inputs are same, that output value is excluded. I mean, that is not taken, that becomes 0. So is exclusive OR is like this. When either one of these two input is 1, then that value is the output. And XOR is not in this problem, but still I have shown here. This is our inverts the output of the XOR function. XNOR, just for the sake of clarity, I have shown here what is XNOR, but it is not the part of the problem. So let's visit to our ladder program. Okay, so I have a problem written in this project 3, PLC project 3 main program. Let's open it and call a network and write it example 4, and call that function example 4. I have written it example 4. Okay, now I called the program inside OV1, which is the main programming block, If I double click this one, this would open example 4 function. Now, as usual, if you have followed my example 1, 2, 3 uh, problem solving video, previous videos, I have this method of reading the digital input from the module and saving the status into block. That is, all DI block is used to save the digital input statuses. And then onwards, I use this data block values into my program and execute the logic. Because in this example we don't have any outputs, so we are not going to use the output, writing to the output modules. But let's go to the problem again. As you have you know this, the precedence of the order is and then or and then exclusive or and then complements. So complements has the lowest precedence, priority is the lowest. So in in the PLC OB on block, execution is from the first network towards the last network, that is bottom. So if we keep the order in that way, the first network will be actually the lowest priority one. And remember, we are storing the results of all these four operations in single bit, that is bit 1. So that means if first operation executes, it will store the result in bit 1. Then in the same scan, if the second operation also executes, the result of that operation also overrides into that bit 1 as well. So this becomes a higher priority than the first network. And same way, if we keep the AND operation at the bottom of this ladder logic program, then that AND operation becomes the highest priority function, whose output result will override the all previous three other operations. In that way, we can actually keep this order like this. So we will make the complement ladder logic in the first network, and then XOR in the second network. Sorry, it should be here, or and XOR. Oops, it was right. It was that way. This is the right one. Complement is the first network, and then second network, third network, and fourth network. This is the last network with the highest precedence. Is if you follow this one, so I have complement network here, there's two, and then exclusive or, and then or, and then and last network I have executed the AND operation. Now let, you, let us follow the step-by-step process. What is the ladder logic of this complement? Now, the logic is when the input DI4 is pressed or energized, then only the operation should, happen. The complement operation should happen. Now, to do that, we have to filter out when it is not pressed, because when it is not pressed, we are not checking the result. This is common for all four operations, where we are not pressing any digital input 1 to 4. We are not executing any of the logic. So actually, we're going to skip that state, whatever it is. So in this network, what I did, when DI4 is not pressed, not energized, we are going to skip that result, getting the result, or even scanning this section, complement ladder logic, and checking the next available operation, that is exclusive OR. And DI3 is used to activate the exclusive OR. Now Here we have used a opposite status checking instruction. This is normally operation in ladder, and this is normally close. What will happen when this input is not activated? It's read like that, not activated, then jump to where? COMPL. This is the name of the level where uh, the scanning will jump to that location. And the program scanning will jump to from here to COMPL, this location, and then it will continue from here onwards. Now here I have used not energize then jump, but in the exclusive OR I have used this one. I have reverse instruction. So if this is on, this will not jump. If this is not on, then this will jump, because it is jump not means if RLO, result of operation up to this, is not on, then it will jump. It's actually same, meaning is same, but the instruction is I have changed this way and that way. This is I have used inverted uh, status, while I have used jump here, but here I have used normally open, but here the jump instruction is opposite, jump not. If the not is the input, then jump. Now not is like actually the inverted logic. If bit 0 is not on, that is off, then make another bit on. It's like reversing the status of this one. But if this is 0, then make this bit 1. So that is complement. It's simple to follow. But this will only happen if DI4 is on. If DI4 is not on, then remember we have a ladder logic written before this, and that will uh, make skipping this ladder logic part. This part will be skipped to here. So this will become irrelevant now. Now the second exclusive OR part is like this. You have bit 0 and bit 2. Between these two bits, the exclusive OR operation is stored. The result is stored in bit 1. So when this is on, this is off. This will be on. And when this is off and this is on, this will be on as well. In all two other uh, cases, this will remain off. So this is exclusive OR, and then OR operation similarly will happen, will be executed when DI2 is on. If not, it will jump to OR this level, that is OR skip. Now in this section we have this OR operation between bit 0 and bit 1, and this is standard OR operation in ladder logic. So if either of these two is on, or both are both two tags are on, then this bit will be turned on. And then AND operation. Now AND operation is like in series two normally open contacts are connected. Same thing, DI on activates this AND operation. So if it is not on, then we skip to end of the program here and skip. And here arbitrary operation is being executed. So if this bit 0 and bit 1 both are on, then only the output will be 1. In any other case, this will remain 0. So this is all for operation in example 4. There are some extension to this example that we will do in later part of the videos in in future video will cover up that. So here is few extra practice. Solve the above problem without using jump and level. Solve the above problem using function block instead of function. And what's the benefit? Can you create instruction of boolean and or XOR not to use in ladder using function. And number 4 is, did you find any mistakes in the given ladder logic? This is about example 4. So hope we can quickly test this operation whether it's working or not. Let's open our watch table. This is the 3 bits we need for testing, and we have to download it. Let's go offline and then download. I have already opened the simulator from here. Simulator, if you click on the project and then start simulator, and this will open simulator like this, and then you can select the project and download. Before download, of course, you have to compile it so that the updated compile you can do from right click and then go to compile only changes or rebuild all hardware and software, and software rebuild all either option. You choose whatever applicable to your testing, and then we download. And here we have to give input I 1.7, I think I 1.2 or 3, okay, 2 and 3 4 5, okay, 2 and 3, and the last input is 4. Go online. The first operation, let's do the NOT operation, that is this one. So NOT, we are using the bit 0 result stored in bit 1. So if we make this one 1, so you see, because bit 0 is false, bit 1 is true, because this is a complement operation. Now make it true, it will become false. Make it false, it will become true. So NOT operation is working, right? But if I turn off this one, this remain the result remain the last value. Okay, so this is one thing to notice. Now I keep this on TI4. This is the lowest priority digital input. Then next, above this one, little bit higher priority is this one. This is exclusive OR. Sorry, turn on this one. Okay, so we turn on this one, and this is exclusive OR. That means, and we are doing this between 0 and 2. Bit 0 and bit 2. So either bit 0 or bit 2 should be 1, so that bit 1 should be true. Let's turn on 1. Turn on this. You see, I turn on bit 0 and then bit 1 become 1 as well. If I turn on both bit 0 and bit 2, you see the bit 1 turns false, because as per our table, exclusive OR table, you see, if both are on, then output also 0, and both 0 obviously 0. This output is on only if either of these two is on. Now if I turn off this one, you see output become 1. So exclusive OR also working, and this is higher priority. That's why our bit 1 is the result of exclusive OR, not the result of complement. And then let's turn OR operation. Turn on OR operation, and OR is between bit 0 and bit 1. I turn off this one. Okay, so bit OR between this and this. So if I make OR, that means this or this. If any one of these two bit is on, that bit 1 will be on. Let's turn on this one or this one. It's not turning on. If I turn on bit 0, this turn to 1. If I turn off, it turn off as well. So it's happening. Now the thing is, we have a problem here, because in ladder logic bit 1 is repeatedly used here as a, and this will make latch the output. If I turn on this one from here, it's supposed to latch this and remain on irrespective of this operation bit 0 value. So I will correct that in another video, how we can prevent that. So that's why it's not allowed. It's turning on and then goes off immediately, because there are multiple operations going on. Okay, so this one is working. We can do one thing. For this moment, we make this bit 0, bit 2, sorry, bit 2, and then download. So OR operation between bit 0 and bit 2, and result is stored in bit 1. So in that way, it will become very easy to test. Now turn on this or this, the result will be in bit 1. Turn on bit 1, the result is here, is on. Turn off and it's turn off. Turn on bit 2, the result is in bit 1, that is on now. Turn off, it goes off. So now the OR operation is perfectly working, and we can move forward to AND operation, that is DI1. We turn on DI1. Now the DI1 is between bit 0 and bit 1, and the result is also stored in bit 1. And this is a problem, because it will not happen if you turn on this one, and if you don't turn on this one, bit 1, it will remain false. If you turn on this one and don't turn on this one, this will remain false. But if you turn on this one and turn off this one, this will also turn off the output. So it's not the correct programming. We have to change it to bit 2. We will change the example. There is some mistake in the example. description. We used to do mistakes, but this is a very silly mistake we did. Anyway, now the AND operation is between bit 0 and bit 2. The result is stored in bit 1. AND operation is activated. Let's turn on this, and this output is on. Turn off any of these two, output will be off. This output is off. Turn on again, and now this turn off this one, output is off. Okay, so the AND operation is working perfectly fine. And hope this demonstration and this simulation understood by all of you, and hope you can do very nice programming. Thank you and see you.